All right, welcome to the talk. I'm Helena Edelson. I work at DATASTAX, and we basically run Lambda architecture over Cassandra. We have some of the main Cassandra committers. Real quick about me, I am a senior engineer in analytics at DATASTAX. Previously, I've been for years a senior cloud engineer working on cloud automation at VMware. Worked on cybersecurity and big data projects, and probably before that, like a decade of messaging. I'm also an Akka contributor. I've written some new features for Akka cluster, and I'm a primary committer to the Spark Cassandra connector. And I've been writing Scala in production since 2010. So the two slides on the background are how I came to all of this. When I was at my last company, it was a security company. I was tasked to write, we had some Hadoop APIs, I guess, that were in Java, some of them Python, basically using Pig. Everything was obviously just batch. And I was looking into scalding, which is it's a Scala API over cascading. And so I wrote a fully automated, our first Scala pipeline in scalding, which is really nice, and that's just a basic example of what something like that would look like. Things like that pale source, that's so that we could work with Hadoop sequence files. And it was very concise, it was nice, but at the same time, it was just batch. And also at the time, there wasn't any kind of integration with Cassandra, so I had to write my own Cassandra tab because everything I've been doing for several years has been working with Cassandra and big data. And then after that was completed, I moved to a new project where I moved back to what is really my normal environment, development environment, which is asynchronous applications in Scala using Akka in the cloud. And I didn't want anything to do with Hadoop, but it was going to be a massive big data project, basically pooling together data sources from a greatly disparate amount of data sources with very, very different data structures, which is something that Cassandra is very good at, to work with flexible data structures. And so I started looking at Spark, and I just was pretty amazed. It seemed like a little bit of a challenge to get up and running, but then once I actually looked at it, it really wasn't. So this is just a very basic sample of a very simple Spark word count. Compared to scalding, it doesn't really seem that much different. In this sample, I abstracted a lot. In this sample, I abstracted a little bit, just the basic setup of Spark, but it's still very, very concise and clean. And it was nice because I could write this in my Akka applications, which I'm going to get to in a little bit, but that abstracts a lot for me as well as an application developer. And the nice thing about this was that I didn't have to interact with Hadoop anymore. So breaking the talk down, what we're going to be going into is the overarching concept of delivering meaning in real time in our analytics applications. And then I'm going to go into, and the challenges that presents. And then I'm going to go into sort of a breakdown of each of the technologies I'm talking about, and just to give you a sense of why these specific ones. Because there are many options, and they're all very good. But you do have to really think about your use case and pick your technology stack pretty wisely. And then I'm going to go into a bit about composable pipelines, putting all of these together with some really nice code samples, and then a sample application, and then I'll direct you to all of this information afterwards. Also, I have a lot of territory to cover, so if we could possibly hold questions to the end, and if there isn't time at the end, I'm very easy to reach. You can ping me, and I'll give you a bunch of information on how to ping me with questions. So I saw this quote recently, so I just snuck this in there yesterday. Sending data between systems is difficult, was what I saw. And I thought, I don't know that I any longer can agree with that. I can't say that it's difficult on the application layer. Ops has its own challenges, but on the application layer, it's now very, very easy to transparently bring all of these technologies together to do our big data analytics applications. I think now the problem is really about managing risk and the strategies that enable us to do that. And as we go into the talk, I'm going to show you a lot of ways to easily do this. So regardless of the meaning we're all searching for in our vast amounts of data, whether we're in science, finance, technology, healthcare, energy, we all share the same problems that have to be solved. How do we achieve that? What are the hurdles? What technologies best support our requirements? And I love this cartoon. And some of the common strategies, we need all of our technologies to exhibit and support these basic bullet points. There's, of course, many others, but these are very, very high level. And so being able to pull together technologies that actually enable us to do that more easily and focus on our business logic is, it's difficult, but I mean, I think personally that this is a pretty good stack. But again, I'm not preaching it. It really depends on your particular use case. And you might need to tweak something like this. So a few weeks ago, I made this really nerdy chart where I looked at all of those technologies and wanted to compare them to all of the specific technologies that I'm going to talk about. What do they all exhibit? And if you compare each strategy to the technologies, either individually or in collaboration together, they all exhibit them, and that's pretty cool. Fault tolerance, failure detection, fast, low latency, distributed data locality, which is a really big one, masterless, decentralized cluster membership, being able to span racks and data centers, being able to hash the node ring, partition aware, parallelism, and network topology aware are some very important features. Oops. Lambda architecture is something we're hearing a lot about. There's many different parts to the description, but just looking at one of them, it's one of the most common is the integration of batch and stream processing together. And Spark actually is one of the few frameworks that allows you to do that in the same application pretty seamlessly, and you'll see that in some of the code samples. You need to be able to roll back to given historical points in your data in case of failure, rebuild from immutable data, and being able to handle petabytes of data. So here's a pretty common use case that we see out in the field. I need fast access to historical data on the fly for predictive modeling with real-time data from the stream. So we need to look at our current data stream against the historic data. I also need to be able to mix stream and batch in the same applications. So how do we do that? One really useful tool is to be able to integrate Spark. So first of all, let me find out what kind of background you guys have. Who's familiar with or working with Spark? Raise your hand. And how many of you are doing it in production? Or still, yeah, cool. How many of you guys are working with Kafka? Great. And Scala? Excellent. One more, Akka? Okay. Spark distributes your data across the cluster. It's a fast distributed, scalable, fault-tolerant cluster compute system. It works well with gigabytes, terabytes, and petabytes of data, works well with different storage media. It works well with low latency streaming jobs and long-running batch jobs, easily join disparate data sets from different sources, and it does not require running Hadoop, which is a big win. Kafka, a high-throughput distributed messaging system, really good at handling massive data load. One really nice way to use it is to help provide some back pressure for dealing with large event spikes. Really good at with communication in between different components in large distributed systems, and has excellent fault tolerance built in. Now I'm really doing the drive-by version in this, just basic, like boom, 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 here's all the technologies, and then I'm going to go into some of them in detail. And this is what sort of architecture might look like, but more so about the flow of data, where you have all these different applications, and they're different data sources, different use cases, funneling information collected into Kafka. And then Kafka being all the consumers on the back end, being able to asynchronously pull data out and process that and do other work with it. So we have a lot of distributed producers, a lot of distributed consumers, everything coming and going up at the same time. So on the back end, you might have monitoring, event behavior tracking. You might have your applications handling data processing, analytics, machine learning, and all of that sitting on top of Spark, something like the Spark Cassandra connector, which I am going to get in detail into, and being able to store data very quickly into Cassandra across multi-data centers. So the one thing you can count on in your infrastructure, everyone's probably familiar with Chaos Monkey. Oh, I had a little animation. It's gone. Bummer. Anyway, what I've found over the years is, and if I can do it right. Oh, that's weird. Oh, I have a little bug. One of the things I've found over the years, given something like Chaos Monkey in large distributed systems, is that I've never found Cassandra to go down. It is literally always on. No matter, you can have a whole data center go down and your applications are still running. Sorry, this is my little problem. All right, so what is Cassandra? It's a masterless multi-data center NoSQL data store that is network topology aware. It is always on. You can lose entire data centers and your applications still run. Automatic data distribution. Your data is transparently partitioned. You get customizable replication, storing redundant copies of data across nodes. Excuse me. It's a transactional database, and it's incredibly fast. So how can we encapsulate all of this data processing in our applications with all these different source sinks into our application layer? And Akka, I found, is incredibly useful for many reasons. And I'm going to get into that in a bit. And what do they all have in common? Does anyone know? Venture a guess. You win. Yeah, they all are written in Scala. And there's many reasons why, for example, Spark being written in Scala, why they chose to do that. One reason is because Scala has the ability to capture functions and ship them over the network. Also, Scala's static typing makes it a lot easier to control performance compared to some of the other JVM languages. And I will say, I'm sure we all work with many different programming languages here. Akka is only for the JVM, so sorry, Python users. Akka is a framework for building scalable, highly concurrent distributed JVM applications. It abstracts all of our concurrency, which is huge. I don't know how many times you guys have had to do your own boilerplate concurrency work, but it is really horrible. It also enables us to work within an actor model, which as far as our application design, really helps with encapsulation. It gives us a clean, configurable, fault-tolerant strategies that we can easily cater to whatever we need to do. It gives us, because of the actor model, a really nice abstraction for the hierarchy. So we can set up our own supervisors for many different workers. We can very easily spin up, a load-balanced router that handles load balancing to 20 different worker actors. Very, very easy to do. So wrapping all of these together, and this is what we're going to get into, being able to stream data from Kafka to Cassandra, stream data from Kafka to Spark, through Spark, and write that to Cassandra, reading and writing to Cassandra in the Kafka stream when you need to look at data in the stream and compare that with some historical data. And the nice thing about all of this is that you don't need to do, how many times have I said that so far? Sorry. So just a quick what that kind of architecture might look like, where you have your code sort of on the top tier, all of the different configurable modules of Spark that you can use, your Spark core sitting over Akka cluster, and at the moment, and I believe that this is going to change, Spark already uses Akka and Akka cluster internally, but I did hear that they're going to change that just because I think they really like it, but it's hard to keep that private from other Akka users that maybe want to use the latest version. And the way it is now, the Spark code has to, they have to try and keep up to date with Akka, and it's just been sort of taking them away from other new features that they need to work on. So on top of that, we're dealing with our Apache Kafka cluster and then Cassandra. Okay, getting a little bit into Spark. The core modules of Spark are Spark Streaming. Well, there's Spark Core, of course, and then Spark Streaming for high throughput, fault-tolerant stream processing, working with real-time data. And when I say real-time, I mean I'm going to explain that when I get into Spark Streaming, but it's not quite the same thing as working with Storm streaming. It's a little bit different because you are basically setting up micro batches and windows of time that you're looking at. Spark SQL lets us do queries with Spark SQL, and now you can also integrate Spark SQL with the Spark Cassandra connector. I'm going to show you some code for that. Native machine learning through Spark ML Lib, and I think I have 2 slides on that for you for code. And Spark GraphX for graph processing, and I believe that the Spark R is still in alpha. A lot of people think that Spark's a new project, and I think in terms of IT, it's actually not. It's been around for a few years now. It's also one of the most active open source projects in big data, with over 200 contributors and at least 50 different organizations around the world. So a recent release represented the work of 172 contributors with more than 60 institutions and more than 1,000 individual patches. So it's very, very active. People are just, adding and working on this very, very rapidly. And they do releases every 3 months, so they're very good at quickly adding new features for users. Using the Spark API, it's incredibly easy, especially if you're coming from Scala already and you're familiar with working with Scala collections. It's in a large part kind of the same sort of API, but it, of course, still allows you to do all the MapReduce work that you need to do over your data. So here's 2 functions doing top K. One of them I have just as a sample where you can call, this is, if we already had the Spark context created, and I'll show you this in a second, we can call the function parallelize, and this is in Spark Core. Pass in any kind of data collection that we have, and then I can call in the Spark Core API top K, give me the top 20 of this data set, and then I can call something like collect. But there's also, really important, I use this more than collect, is collect async. So that can allow me to do the processing across the Spark cluster and give me all of that in a future. So I'm not going to be blocking any threads, and I'm going to show you some code samples on that too. But another really nice thing about Spark is that it allows data scientists to bridge the gap, the engineering gap, and it allows engineers to bridge the data science gap. So like I can do some things, for example, with machine learning and not have to have spent 4 years in school studying machine learning. I mean, obviously I wouldn't know what a data scientist would know about that, but I can go ahead and implement something. And the thing to note in this example when we're looking at the collection processing is that we're not just doing like a seek.max kind of function that you would on Scala collections. What we're doing actually in this parallelize function and the top K, we're working with our data across the Spark cluster, so everything is in fact parallelized. And it's not really just a MapReduce API. It actually allows you to do quite a lot. And I'm sorry that's so tiny, but I just wanted to shove all of it in there so you could see it's a very robust API. Here's a very basic Spark word count. So we set up the Spark conf. And the Spark conf is what allows you to, from the system, or there's several different ways that you can pass in your configuration. But that's where you pass in, your Spark master. You could pass in any of your own custom configuration that you need to get to your own applications. It's very, very flexible. And then with that Spark conf, you create your Spark context. And then once you have that set up, you can start doing work with Spark Core. And so here we're just saying Spark context, calling the function text file. I'm slurping in a bunch of information where I'm going to do a basic word count. I flat map over that data to parse it all out into a collection, and then I'm going to map my word and my start being able to do my count on that and call reduce by key, and then I call collect, which is actually going to give me that data. One of the nice things also about working with Spark is you can get up and running very quickly. You don't actually have to go and write an application before you can start working on it. It comes with, and if you're familiar with Scala, it's just like the Scala REPL. They have their own version just built on top of the Scala REPL, but it's a Spark REPL. So you can start it up, and it automatically creates Spark conf and the Spark context for you. So you can immediately say, here's my collection of ints. I have an array, and I'm going to pass that collection of data into the parallelized function. And what it gives me back is a RDD, a Spark RDD of my data of int. So it's very easy to see how this works on the top level. Breaking down the kind of RDD operations that you can do, there's transformations and actions. And the transformations, all of this happens lazily as far as the Spark executor goes. So you basically instruct it on what you want it to do over your data. So here we have transformations like flat map and reduce by key. And then we call one of the actions to actually say, OK, now let's execute this, and executes it through the Spark executor across the cluster when we call collect. You can do collect, you can call collect async, print if you just want to print the stream of data while you're debugging things, or one of the other things. You can save things to sequence files. I'm going to show you how to write the data to Cassandra. There's many different types of actions where you're actually now executing and getting the result of that data. So I think I have a few slides on Spark streaming when batch is not enough. And I think for myself, this is one of the cooler parts of it because it allows me to really do event-driven asynchronous applications, still being able to do analytics without Hadoop. Very, very useful. So it helps us easily integrate real-time data from disparate event streams in event-driven asynchronous, scalable, type-safe, and fault-tolerant applications. And that is very different conceptually to that first slide that I showed you with that little scalding piece of code, that scalding Hadoop job. That was not in a fault-tolerant application. It's just a scheduled batch job for reporting or something. Very, very different. So this is a huge difference from the single-threaded procedural data analysis and computation that over the past decade or earlier. And perhaps one of the nicest features about Spark streaming is it has exactly once message guarantees. So basic setup of Spark streaming just looks like this, where we create our Spark conf, and then we create a streaming context instead of the Spark context that I just showed you. And then I'd be doing a bunch of my computations in the stream. And then if you're going to set up a lot of really long windows, and I'm going to show you that in a second, I probably want to do this Spark streaming context, set up a checkpoint for fault tolerance, and then you call start, and then you would call await termination, because again, we're not in batch land anymore. We're saying this is just going to keep running for days, weeks, whatever. And so how does this work? With Spark streaming, with Spark, we have the core RDDs, and then Spark streaming takes those RDDs, and we're working now with a DStream, which is basically micro batches of that. So data is received during each interval, and it's stored across the Spark cluster to form the input data set, which is what we call the micro batches. And once that interval completes, this data set is processed through parallel operations. So that's your map, reduce, join, and window operations. And then with the DStream, we can ingest and process the data with complex algorithms that are out of the box in Spark. I lost somehow, sorry, a lot of my this slide is actually supposed to animate all of the different data sources. Somehow I lost them, but it's it's Cassandra, it's like 0MQ, it's Hadoop, it's Twitter. These are all of the input-output data sources for Spark streaming. Kafka, which I'm going to go into quite a bit. Yeah, animation lost. Sorry. Okay. Oh, it is? All right. And then on top of those DStreams, we have in the external directory of the Spark repo several different options for all of those different data sources. But built in are the basic types, which are being able to stream from, for example, sockets. There's an HTTP streaming receiver. You can stream from Akka actors, from S3 buckets. That's all built in. And then in the external, the more advanced receiver input DStreams are things like Kafka, Flume, Kinesis, Twitter, 0MQ, and a ticket that I'm working on right now is being able to stream from Cassandra. So you can subscribe to events happening on particular Cassandra tables and stream that data, hopefully coming soon. So here's just a basic streaming example using the FileInputDStream, what that looks like. And again, it's just doing very basic stream from, it's basically Spark streaming is listening at the particular S3 bucket that you tell it to. We pipe it through our calculation, breaking the data up, mapping it. Here I do a count by value, and then here I'm saving it. Sorry, save as object file is going to basically generate the data at the end of the computation into Hadoop sequence files for me and save that in my output S3 bucket. And look how much code that is. It's really, really concise. There's a lot of streaming window operations that you can do as well. This is a very, very basic one where here I'm trying to reduce the last 30 seconds of data every 10 seconds. So I set up my window length, which is the duration, and then I set up my sliding interval. So that is the interval at which the window operation is performed every 10 seconds. So I'm doing my streaming window operations on my data, and then when I'm done with the computation, every n interval, save that data to the particular key space in Cassandra table. Again, very concise. A few slides on Cassandra. This is just a quick slide on some of our the public-facing customers at DataStax that I can actually show. So like I said, we deliver Cassandra as a platform, working on providing a very easy deployable Lambda architecture for users so that it takes all the pain of administration away. Integrating a lot of open source technologies on top of Cassandra instead of things like Zookeeper. So for example, Netflix uses Cassandra with our DSC product. They process 1 trillion transactions a day through Cassandra over 1,000 nodes across many, many data centers. The Weather Channel is a huge Spark user. They run Spark over Cassandra to analyze real-time weather data. Or Apple iCloud, they use it for maps. So this is my 10 things about Cassandra slide. So with Cassandra, there's no concept of master or read replicas. We test 1,000-node clusters every day for days at a time. Structured and semi-structured, unstructured, and dynamic data. Adding a column to a table will take the same time as a row of data or a billion. It's very, very fast. You can add new nodes automatically. They'll do it themselves, adding to the cluster. There's a lot of different DataStax drivers, like the Java driver. You can use Python. The Scala driver is coming soon. And I think there's more. I know there's a Node.js. There's some other one I can't remember, and I think Closure came out or is coming soon. So there's quite a few. All of the drivers discover new nodes automatically. You'll never have to shard again. Every write is durable. Replicating across multiple data centers provides lower latency, so you can survive outages. Nodes down does not equal a database down, and a data center down does not equal a database down. Some of the use cases. A big one is for security, real-time security processing, a lot of information with handling machine learning and storing that data and reading back from Cassandra. I like that slide. Also things like for scientific data, for example, astrophysics, they need to be able to process a lot of data. Storing all of that in Cassandra, for them, it's very easy, or particle physics. Genetics and biological computations, again, a lot of data to process, different data structures, very easy to do in Cassandra. And a big one for us too is IoT, where companies might have, like an energy company might have a large distribution of sensors around the world or within their zone and need to, or advertising companies might have a lot of different devices that they need to interact with and store the data for those. So that's another big one for us. So with Cassandra, the availability model is from the Amazon Dynamo paper. If anyone has ever read that, it's a good read. It's distributed masterless, and the data model comes from the Google Big Table work. It's network topology aware, multi-data center replication. Using Spark over Cassandra, there's a few ways that Cassandra actually enriches Spark, which is pretty cool. Like Cassandra enables Spark nodes to transparently communicate across data centers. Handling failures, if a node goes down, in the background, everything's doing asynchronous replication. And when the node comes back, it uses things like hinted handoff. Gossip protocol, which it uses internally so that each node talks to a few of its peers and shares the information. And then consensus, being the agreement among peers on the value of shared piece of data. And Cassandra, for consensus, we use the Paxos algorithm. And you can even use Cassandra to avoid adding Zookeeper. And who would want to work with Zookeeper? I've had to. It's kind of a pain operationally. Cassandra CQL, it's very much like SQL. So as a developer, it's very easy to get up and running with. But it does, because of the nature of Cassandra and how it does things differently for the vast distribution that it can handle, it does have quite a lot to the CQL language that allows you to leverage speed in your data model. And I'm going to show you some of that. But as you can see, it's pretty familiar syntax. How many of you are working with time series data? Yeah, it's usually pretty popular. And that's something that Cassandra has been doing for years. And it's actually built into Cassandra to be able to work really easily with time series. So for example, and I have a second slide later on that goes into this a little bit more so that you can see kind of the real value of it. But just on the surface, here we're creating a table, whether it might be my key space and my table raw data. I set up my primary key, so I'm using clustering key columns for the primary key. And then I set up my Cassandra clustering columns with the clustering order by. So what I'm doing is I'm telling Cassandra that every time I do a write, I want you to automatically keep the most recent on top. So you don't have to handle doing any of that in your Spark computation. And sometimes those function calls can be very heavyweight. Very expensive, so having Cassandra do that for you is very nice. So you don't have to handle that on your client code on the write or the read. You just let the Cassandra cluster handle that for you. So then when you need to get the data back on reads, it's automatically going to give you the most recent at the top, order everything for you. And that sort of just gives you kind of a peek of the importance of being able to leverage the doing the right data model when you're working with Cassandra, because it can give you incredible speed boosts. And we have some experts in that at DATASTAX that are very, very willing to help people. And if you are working with any of these use cases, please ping me, and I will put you to the right person that can help you take advantage of that. So I think this is my last slide on Cassandra specifically, and then we're going to start getting into some code finally. So another part of working with Cassandra for time series is just the time UUID concept. And this is something that you do have to be aware of when you're working with very small windows of when events are being written very, very quickly, and often the timestamps can be the same, and you're basically going to be overwriting data, which is a no. So you can leverage, here I have the time segment field when I say create table, that second line. Time segment, big int, and then further down the TUUID is the timestamp UUID. And so that's going to make sure that protects us from simultaneous events overwriting each other. And then the time segment field is another nice thing to leverage. So that helps us keep, the segment keeps us from writing unbounded partitions. Okay, getting more into the code. So I have a few slides now on using the Spark Cassandra connector. Just a few of the pictured parts, and then we're really going to get into code. So the Spark Cassandra connector helps you read-write data from Cassandra within all of your Spark computation very seamlessly. It's all of the filtering, like your selects and wheres, are all happening server-side. So that's never happening on the client. It's never going to be heavyweight for you. All of the Cassandra types are supported and converted to Scala types. There's a lot of implicit conversion happening, and I'm going to show you how to do that so that you can read data from a Cassandra table, and the connector will automatically just, all you need to do is set what case class that you want it to convert to, and it will automatically convert that your data set to that. And there is a Java API, so that you can work with it that way. We recommend, as far as deployment architecture, to co-locate your Spark and Cassandra nodes so that you can take advantage of data locality. And what that's about in a very small nutshell is Cassandra is partition aware and network topology aware. So it knows all of the different data partitions. And in the Spark API in the internal part, it allows you to pass in the partition information. So co-locating the nodes lets you take advantage of data locality so that when the two of them are interacting with data for specific partitions, it's right there. It's a very, very fast operation. So starting to read and write data from your computations between these two, all you need to do is for basic Spark, do this import, and that brings in all of the implicits. And then for the streaming context, that's what you would want to import. So basic writing, it looks kind of the same as I just showed you in the initial setup for Spark. That's our Spark context. And then I can call the parallelize function, pass in my collection of data, and just call save to Cassandra now. Pass in my key space and table. Or here I can do, and I have a few about these, but usually, you can't do joins with no SQL, but with Spark and the Cassandra connector, you actually can. So here is a basic sample. I have a predictions RDD collection of data. I can call join on predictions for music collection of RDD, save that to Cassandra. So we are joining our data sets. A basic read from Cassandra, so I can call Spark context Cassandra table, and here I'm not specifying the type, so it's just going to give me back the Cassandra RDD, which is just an extension of the Spark RDD, but enriched. And then I have all my server-side row filtering with my select statements and my where clauses. Very, very, I think most people would find that very familiar. This is the word I was looking for. Getting specific rows, so here's where I want to call a specific Cassandra table, and I wanted to automatically or implicitly convert that data into my specific, here is a Scala case class, but you can do this with Java, so it would be your Java beans. So it's going to do get all of your information based on your filtering from the Cassandra table, map that implicitly into, here I've got monthly commits case class, and that's what's going to be populating my Spark RDD. And then from there, do any kind of computations on that I want. Very easy to work with data that's just tuples where you don't have a specific type. So here I just have a tuple of basic types, int, date, and string, and it's going to convert all of the data in the Cassandra rows into those tuples. Or you can do key values. There's really a lot of configuration that's built into it that's very easy. Here I'm calling you can call limit, you can call it take in your processing for your data from Cassandra. And at the bottom I'm showing the with ascending or descending order. But from what I showed you earlier, where if for example you're working with Timeseries, if you set up your Cassandra data model properly, you should never be calling those, because that's an additional operation over a lot of data. So we have it there, but if you set up your data model properly, you wouldn't need to do it. And that's just a very small subset of the functionality. I'm just kind of trying to race through it for you. There's a thing in Cassandra called user-defined types. So I can instruct Cassandra on what type of my own, like an address type, and set that up, and then work with that in my code. Can you even see that? It's kind of tiny, but I wanted to shove a bunch of information in there. But this is working with user-defined types and JSON. So I have a bunch of JSON information, and I have my own custom type called dimensions and categories. So you can easily create those in Cassandra and then store your data using those types. OK, now we get into some better code, and then the application right after that. So this is showing you very basic usage of the Spark, the Cassandra SQL that's built on top of Spark SQL. So I can do queries like this where I'm doing joins on my, this is no SQL. You could never do this before. So I'm doing joins on various tables, and you can even cross key spaces as well. Map it, I can do as whatever highly complicated data computations that I want in Spark. and save that read and write to Cassandra. You can cross key spaces, you can cross databases, and here's an example of Spark SQL with JSON and Cassandra. So I have my, here you create your SQL context in Spark. I have, wherever my source is coming from my JSON data, and then I want to pass it into the Spark JSON RDD, all of that data, do my computations and save that data to Cassandra, and then later on in your application, you can also read that back in with whatever, populating whatever type that you want to. So the Spark streaming, I have a lot of Kafka examples to show you. This is just the first one. This is using the, creating a Kafka stream. So that's that receiver input D stream that I showed you earlier. I'm passing in the Spark streaming context. That's that SSC. I pass it, all of the Kafka params that it needs, whatever topic maps, if I can have one or multiple Kafka topics that I want to work with, specify in Spark what memory level I want it to use. I map that in here. I'm just saying, drop the key, just give me my JSON data, and then just using a basic API to change that string of data into my actual type, monthly commits, my Scala case class. And then I want to save that data to Cassandra. So this is all happening in the Kafka stream asynchronously. And then I can do in the SQL shell just to select all from my key space, my table, and take a look at the data. So it's pretty, again, it's really concise. And the thing that's important about concise code is there's less testing and debugging. It's all just right there. So we're working with Spark streaming now with Kafka and Cassandra. I set up my Spark streaming context. I create my Kafka stream and do whatever computations with that and save that to Cassandra. So you can do it with Spark Core and Spark streaming. Here's with the external Twitter and Spark streaming. So I call Twitter utils, create my asynchronous stream from Twitter, pass in whatever filtering that I want to do, and do my computations based on that data as it comes in from the Twitter stream. Here I'm just I'm specifying, I want to look for a certain number of hashtags maybe, breaking all of that text in a tweet down into a collection of data. And then from that, I'm just saying if my tags are in there that I'm looking for, grab those, and then I'm doing this count by value in window. So every 5 seconds is my window. I want to look at that data, and then do any kind of transformation over that data, and then I want to store that into Cassandra from the stream. And here's just a basic example of doing a read-write. So going back to, if you remember that one of the first slides where I showed the lady shopping and being able to do predictive modeling, where you need to get your information in the stream and at the same time be able to match that against some historic data so you can actually do some processing. So this is kind of doing that with kind of a security idea. So here I'm pulling data asynchronously from, receiving data from my Kafka stream. Then I am going to, in that stream processing, I'm going to look at historic data that I have stored in Cassandra. Say I have a security event that I've detected, it's come into Kafka, and then I want to see, look at my previous stored adversary attacks. Is this an adversary that we've seen before? Looking at the origin, I want to look at like some tag on the adversary name or something and what kind of specific security attack type it is, something like that. Grab that data, and then probably there'd be a lot more processing of that, and then eventually save some of this profiling to my adversary profiles table. Simple, right? 2 slides on Spark ML Lib. So with Spark streaming, they have Spark ML Lib is a separate component that you can use or not use. But now you can integrate the Spark ML library with Spark streaming, with Spark SQL, and there's more stuff coming for that. So basically you have the way that it works, the general kind of workflow of it is you have your training data, then you proceed to do the extraction to analyze your data, the specific behaviors that you want to look at. And then you train your model to predict, and then you go into the model testing. So here's just a very basic example. I want to train, here I'm using linear regression model of the streaming data. So the same setup I've been showing you so far. Say my data is coming in from my Kafka stream asynchronously. I've got test data that I just read out of a Cassandra table, and I want to train that using the stochastic gradient descent to update the model based on each new batch of incoming data from that D stream. And so with that model that we set up, I think the only thing that's required there is that function call to set initial weights. And I used vector.dense, but there's a lot of different ways. It's very, very configurable. And again, this is a very, very simple Spark ML example. But, and then once I've built that model and I'm able to compare it from the training stream against the test data, and then I do my predictions based on that. And here I just threw in a save to Cassandra, because once you have your predicted data, you can store it for further aggregation later on. All right, this is getting into the last part of the talk, just a sample of what this might look like in an application, particularly here, what it might look like in a Akka application to do all this work, which, again, if you've had experience writing batch Hadoop jobs, this is great because it's incredibly different. So this is a time series data application working on weather data, where we have streaming weather information coming in from weather stations around the world. We are going to be looking at, real-time data. We're looking at historic data. We're doing aggregations on the streaming data, aggregations later on where we need to, in the stream, look at that new data against the historic data, and what might that actually look like in an application. Something I keep meaning to do to add to this application is add some predictive modeling, but I haven't had time yet. So working with Cassandra, one of the things that you do want to step back and consider compared to relational databases is that your data model should look like your queries. So you really need to think first about, what does my application need? I want to, what do I want to get from this application? Get an ID, data by ID, get data for a single date and time, compute and store and retrieve data monthly with annual aggregations, and then what I want to be storing in that application. And based on that, because again, Cassandra is all about speed with massive amounts of data, so you definitely do things differently, but that's where you get the benefits from it. So for example, creating this table temperature and various inserts of the data, it looks pretty similar to SQL work. So on the larger scale architecturally, what this might look like that I'm going to talk about is I've got several different source applications that in their own ways are gathering information and then sending that into Kafka for, maybe I'm using Kafka for back pressure, and also because I want my backend applications to be able to process that asynchronously. So then on the backend, those are my consumers pulling the data or receiving the data off the Kafka topics. And then in there, once we have that in our processing applications, we're in the Spark computation layer, working on our data through the Spark Cassandra connector. We're able to store and retrieve that data in our processing stream. And then we can even send some of that data aggregation back to requesters, all asynchronously. OK, so here's an example of, on the front end of that application, where I might have a Kafka producer. This is sending data to Kafka. And here I'm just doing it in a very basic Akka actor. And this is a very simplified version, but actually the code in my application looks a lot like this. It doesn't, you don't really need to do that much to do this work. But here what I'm doing with that supervisor strategy, and you can see this is my Kafka producer extends actor. That's the Akka actor. And then I set up my my custom supervisor strategy. So I can say, for particular Kafka exceptions that might arise, this is the behavior that I want to do for my fault tolerance. So this Kafka producer would likely have a hierarchy of supervisors in your deployed application. And so this is going to say, if this actor, if something in there throws any of these particular producers, Kafka producer exceptions, I'm either going to restart, or maybe I want to, for particular exceptions, escalate this to its manager actor, so that there might be different tiers that you want to know how to actually process errors. So that's kind of nice. It's very configurable. And what I've done here is just wrapped this Kafka producer is just a custom Akka actor that I have wrapped so that this guy doesn't even need to know anything about Kafka. It just sends messages. This is a custom type that I wrote, just a case class, a Kafka message envelope, and it can take one or many of a collection of data that I want to just publish to Kafka. So everything is happening completely asynchronously here. So we've got fault tolerance, we've got encapsulation. It's really just know one thing, do one thing, and that really helps as far as application design. Here, of course, once we're publishing things to Kafka, and there might be also some aspect that needs to handle REST requests of data. Maybe we're passing some JSON data into the system. This is an Akka actor as a REST endpoint. So here I'm using the Akka streams and Akka HTTP, which is written around Spray. And so I've got my actor, and I'm creating my flow materializer, and I'm setting it up to bind on a specific host port. And then in that receive function, because every actor has their own implementation of when it's asynchronously receiving specific types, because if you look in the receive, that you have to think of that as far as Akka goes, that is this actor's API. That is not going to retrieve any other data except messages of type HTTP server binding messages. If nothing, like if there's a different data type sent out to the Akka cluster or the particular Akka nodes or actors, and you don't have that type defined in a receive message function, it's just going to go to dead letters. It's just going to, hit the event bus, and it'll log it if you want it to, but that's about it. Anyway, so once it receives this information, it's going to process this in the source and set all the information up for handling, and it passes it into the request handler, and that function is up at the top, kind of. So in that request handler, I can set up various REST paths, the URLs, and say, for this, capture it only if it's a post with this particular path. Maybe that's going to help me define the types that I want to handle. It's a million things that you can do with this, incredibly customizable. Here I'm just showing one. So I want to handle weather. It's version 1 of the API maybe, and I say this guy's only going to handle hourly weather data. And then I have some custom functions that I wrote that takes that information, one or many chunks of data, processes it, and then it sends it off this. If you see at the top of the actor where I say class HTTP receiver actor, and I'm passing in this actor ref. So what's nice to note about that is it's very easy for testing. I can pass in any instance of that actor ref and have it be some kind of probe to handle. So it's very nice in that regard. But here I'm passing in the Kafka publisher that I just showed you. So if it's of this particular type, it's hourly weather data that we're receiving from, it's a REST endpoint, then I want to publish it off to Kafka, and it wraps it in the Kafka envelope and passes it off to Kafka for me. So that's kind of one of the client sides of how you could do things. And again, it's just a really simplified version of many, many possibilities. One of the things I have on the client side of the application, I'll show you the URL where you can pull this, you can clone the repo from GitHub, and it's runnable. There's a big description of how to use it. So here, I like to call things a node guardian, where the thing that actually starts up the actor system on all of your nodes is kind of your root supervisor actor. And this is where here's the example of where I'm creating a router, and I'm using a balancing pool. This is all the Akka API and Akka routing. So I create a balancing pool of any kind of size. Say I want, I'm going to be doing a lot of work here, and I want 20 instances of this actor, Kafka publisher actor. So what it's going to do is balance all of the requests sent to these actors based on whichever one is free. So the key to think about that is, I don't know how many of you have dealt with like slow consumers, or if you're doing profiling and you see like IO await, this is where you can avoid that very, very simply. It's all just built into Akka. And this is a really simple, a really common use case where you want to store raw data right on ingestion, like snapshot it off, and then proceed with all of your Spark computations. So this is an example of that in our Kafka stream. We use that stream, and what's nice to note here is these streams are reusable. I mean, I could pipe everything through one concise function, but here I'm saving it off as the Kafka stream, so I can do many things with that. So I want to save off the raw data to my raw data table, and then I want to proceed with my work. And so I just wanted to step back real quick and look back at the data model before I show you the next slide. So I showed you this first part of the create table earlier, but now in this daily aggregate precipitation, I've got my raw data we're saving off to Cassandra from the Kafka stream. And then what I want to do before the next function call in Spark is I set up my data model. You can see where I made it bold. I said precipitation counter. So there's kind of some stepping around situations in this kind of work where sometimes to do the calculations from the stream against historic data, you need specific parameters in order to do that. And so it gets a little bit interesting to be able to set that up in some use cases. But here it's very easy because I've set up my precipitation counter in Cassandra. And so that means I don't really need any other information. I can just go ahead and do my first aggregate roll-up of that data from the raw data. So once I save off the raw data, then I can, again, reuse the same Kafka stream. It's the same data, just still piping through. And I can, by weather station ID, year, month, day. Let me go back to this really quick. Here, remember, we set up our primary key in the raw data by weather station ID, year, month, day, hour, clustering order by. And this is, again, all time series. That has allowed me then, what that's doing is leveraging data locality, so everything can happen really, really quickly. It's working with the partition that is immediately there. It's not needing to go across the cluster and find that particular partition. So there's some tricks that are commonly done working with Spark and Cassandra that are really going to speed things up for you. Okay, and we're almost done. Here's an example of a temperature actor, and I don't think I showed one of the use cases that I was explaining where you have to sometimes step around things because you need information that you don't have in the stream. But this guy is another actor handling only temperature functions and our temperature computations. It's going to receive only requests for, in this case, monthly high-low temperature, but in the actual code, I'll show you in the repo, it handles a few different types of events. But here we're specifying certain information to pass in to do our aggregation. So here I'm going to do high-low, calculate high-low. And so it's going to the aggregate, the raw data that we've already saved off. And it's giving me, based on some of the parameters, like I have my weather station ID, I have year and month. And so based on that, I can take the existing raw data, do my roll-up of the high-low temperature based on that information. And then I call collect async. Again, I'm doing all this in an asynchronous actor, calling a future. And then once that data comes back asynchronously, I'm mapping that into my monthly temperature case class, very easy. And then I call pipe2. That's a function you can use in Akka. So that's my future. When that calculates and I have the result from that, I'm piping it to the requester actor. So that's very cool. Stuff that you couldn't do before with batching and Hadoop. And that's really it. I have some roadmap slides, but I have no idea what time it is. How much time do we have? Oh wait, let me show you. If you do have questions and want to reach me, you can find me on Twitter. I'm also on GitHub or SlideShare, and unfortunately I forgot to put my email address. But you can come up, and I think I have a bunch of business cards, so if you have questions, you can just ping me later. And here's all the resources. So thanks.